Suppose I'm pushing on two blocks. One block is relatively small, called block A, and it is touching a large block, we'll call block B. And they are resting on, for simplicity, we'll just choose a frictionless surface. And I'm pushing on the edge of block A with some magnitude push force. And my question is try to understand what are the forces, what is the force between blocks A and B, okay, relative to how big this force is and how fast are they accelerating. We'll just basically find a relationship between all those variables, the forces and the acceleration. To start, let's go ahead and draw a free body diagram for B. Okay, here's my free body diagram for B. It's a large block, so the normal force of the surface on B is going to be equal to its large gravitational force down on B. Okay, because I can tell that it's not accelerating up and down, and so these two should be equal. And then I look and I've taken care of the normal force from this interaction, but knowing that it's frictionless, there's no side-to-side force. So the only other force is this contact force at this interface between A and B, and it is pushing it this way. And I'll call that a normal force. It's a I could call it F push or something, but I'm going to call that a normal force. But what's more important, it's A on B. Okay. Now with that, I can see that there is a net force in the horizontal direction to the right, which means there must be an acceleration to the right. Okay, well, let's pause on that for a second. Let's go look at A. So block A, I draw a dot to represent block A. It's a smaller block, so the normal force of the surface on A, which is equal in magnitude to the gravitational force on A from the Earth, because it's not accelerating up and down, so the net force in the vertical is 0. The upward has to equal the downward in magnitude. And the thing that's important here is that block B pushes back on block A with the same magnitude of force as A pushed on B, which is this one right here. So in indicating that, I'm going to draw a force that is opposite in direction, same size, and label it as the same type of force, normal force, and reverse the subscripts, B on A. Okay. So now in doing this, I now can see that these are an action-reaction pair. Okay. They are what we call a third law pair. They are equal in magnitude, opposite in direction, because they are the same interaction. Okay. And Newton's third law tells us that those are of the same size. Okay, so noting those two, I now can start finish this free body diagram. So that is the backwards force on A from B, but we still have this force here. And since A is accelerating forward, okay, then that force must be bigger. Now let me check. How do I know A is accelerating forward? Okay, well, A and B are moving together, and if I look back here, B must be accelerating forward because it has a net force in the x direction. Okay, and since its acceleration must be the same as A, since they're in contact, their acceleration is constrained by that motion, then this must be accelerating forward, which means this push force must be bigger than that. Now, we can do some math in a second, which we will, but what I want to point out is that you might think that the force from A on B must be bigger than this push force, or bigger than the force on A from B, because B is big. It needs a big force to accelerate. A is small. It needs a small force to accelerate. Well, those two statements are true, but that is a second law statement. Second law looks at just one object and all the forces acting on that object. The third law looks at objects or interactions between objects. Okay, so when thinking of the second law, B has a bigger mass, and therefore if it's accelerating at some value A, it must have a big force. And if the little box A, this box A, has a smaller mass, it requires a smaller force to accelerate. But more particularly, it requires a smaller net force. And so we see that the net force, or this force subtract this force, is smaller, it's reasonably smaller than this force, which is the net force on B. And so Newton's second law is upheld. Bigger box needs a bigger net force than this one. And that is true because of this interaction force decreasing this large push force. Okay, so now let's take that and do a little bit of math. Looking at, I'm going to label these to be a little more careful. This is B, this is A. And looking at on B, and then looking at the x component of it, we won't worry about the y's right now. But looking at the x component, you're right, F net x equals mb abx. Okay, which, since they're all moving together, I can reduce that just to one variable, knowing that it's equal for both objects. All right, now what is F net x? It is, there's only one force there, so that is NA on B equals MBA. Okay, let's pause on that, just hold that there. Let's look at A now. Also just focus on the x direction. We have F net x equals MA AX, which again, since they're constrained to move together, the accelerations are the same. We'll just call that A. And then in this case, what is F net x? I look at my free body diagram, I see there's a forward push force, so I'm going to say FP, backwards force here, minus NB on A. Okay, that must equal MAA. Alright, and just a little rewriting. What is FP? It's going to be equal to MAA plus NB on A. Alright, so I can kind of pause there, but let's now think, alright, first of all, this push force we've mathematically shown is bigger than that force between the two boxes by this much, okay, which we established conceptually before. But something I can further do is say, by third law, these two, which are magnitudes, I've taken care of their signs already, but their magnitudes these two magnitudes are the same, so I can insert this in place of this one. Okay, and so doing, I get MAA, oops, let me make that a nice uppercase A, plus MBA, and just gathering the masses, that's MA plus MB A. And so now I've been able to relate directly this push force with the acceleration that these two boxes share, the constrained acceleration. And if I notice carefully, I can come up to something that I really should have guessed before. I get M system times A, which, had I thought about this as the system as one object, then I have Newton's second law for a single object. The external force, this is the only external force, equals mass of the system times that system's acceleration.